Well, thank you very much. So today I'm going to talk about cybersecurity, but I'm going to talk to it from a little different angle than probably what other folks have done today. Where I'm going to kind of talk about the practical aspects of how you actually secure devices within the vehicle. Maybe somewhat technical, but I think that's okay for this crowd. So first, a bit about Lear. This does not work. There we go. So Lear's a tier 1 provider, been around forever doing electrical systems, connectors, wireless technology, you name it, global organization, supplier to pretty much every tier 1 out there. About a year ago, Lear acquired a couple companies. They acquired my company, AutoNet Mobile, who did telematics control units and cloud-based systems, and another company called Arata Systems, who did vehicle-to-vehicle and vehicle-to-infrastructure communications. With that, we formed a new organization called Lear Connexus, and we're really focused around connecting the vehicle. So we build TCUs like these up here, connected gateways, on roadside units, onboard units for DSRC, you name it. And part of our mission has been cybersecurity. We've been delivering connected devices for more than 10 years now, and we're very proud that we've never been hacked. And it's really because we adopted cybersecurity principles from the very beginning. Boom, boom, boom. So these are our principles of cybersecurity. So number 1, security should be built from the very beginning, from the design phase. It's not something you can tack on later. I think that's where a lot of people have gotten stuck before, is they tried to add security as an afterthought. And it's not something you can effectively do. We strongly believe in third-party collaboration. With security in general, it's not something you can do in isolation. You really need to work with your suppliers, your customers, your competitors, and everybody to understand where the threats are coming from so you can fix them. Security is not something that you want to be proprietary with. It's really in everybody's best interest to have secured vehicles. If anybody gets compromised, it really hurts consumer confidence for all of us. In your devices, you really want to log what goes on in that device so you can evaluate and do analytics on that to see where these attack threats are coming from, because they're always new and changing. So you can't just block and drop and forget. You really need to log so you can do the analytics later. Security is something we're never, ever finished with. There's always new attacks, new threats, and you have to have the ability to change your system over the air so you can update your security policies for these new threats. So over-the-air software updates are very important for cybersecurity. When an attack occurs, you need to be able to do something about that. So that's where segmentation and isolation comes from. So if an attack is coming from a Bluetooth interface or a tire pressure sensor, isolate that interface, protect it from getting onto the rest of the vehicle bus or spreading to other vehicles. And then finally, end-to-end validation. Security is not something you can do for just your piece of the system. The systems we deliver, there's half a dozen to 10 suppliers in that. So if we all do security right within our box, that's great. But you really have to validate how the whole system goes together. Because that's where really most of the holes come from, is that integration of components from different suppliers, not having a real understanding of the specification or how the things are supposed to work. So our basic philosophy, block everything. Let through what you know must get through, but block everything else. What you do let through, you authenticate. You make sure it's coming from the person it's supposed to be coming from and the place it's supposed to be coming from. And then you secure it. You either sign it. If you don't care about privacy, you can just sign it. Or if you do care about privacy, you encrypt it. And then you log everything. So next I want to talk about vehicle bus architectures. What exists today and then what we're moving towards. After that, I'll talk about the various security layers, and then security validation, and then some areas where we think we need some improvement in security still. So this is a common vehicle architecture for today. So multiple ECUs sitting on multiple CAN buses. Everybody pretty much talks to everybody with no authentication or security. Even the OBD2 device is a wide open device sitting on the bus. The TCU or the gateways often have some security connecting to the outside wireless interfaces. This is obviously not a good architecture because that OBD2 interface is wide open. Anybody can plug into that OBD2 interface, full access to the CAN bus. They could reverse engineer codes to do whatever they want. So this is obviously an immediate problem. A quick interim solution to fix that many car companies are doing is they're sticking a firewall box in between the OBD2 interface and the rest of the ECUs. And we've got several customers that are doing this today as kind of a rush fix to secure their vehicles. Most of them are using static rules on their firewall, so only let through diagnostics, what's required for emissions, and flashing. Block everything else, and that's good. We're a big proponent of policy-based firewalls, where you can actually change the firewall rules over the air so if you want to decide to let something new through or block something that you didn't anticipate would be a problem. Where we want to get to is an architecture where we have a gateway box that actually does much of security for the vehicle. So this gateway serves as not only a traditional gateway routing functionality for other buses in the vehicle, but it can also house security systems like Firewall. Since it sits on every bus in the vehicle, it's a perfect place to put a firewall where you can have rules about what's allowed to communicate with what. Since it's on every bus in the vehicle, it's also an obvious place to put an intrusion detection system where you can monitor the buses and see if there's any abnormal traffic that you might want to take action against. It also serves as a good place to hold your certificates for signing and encrypting messages, since it talks to everything on the bus and it controls the interface back to the cloud. So this is a model that many OEMs are actually working on today for deployment in 2018-2019 timeframe. Where we really want to get to is this future generation, where we have that same gateway box, but we're encrypting all the messages on the CAN bus. So every message on that CAN bus is either encrypted or digitally signed. Now this creates a few new problems. If every message is encrypted, then all those ECUs have to have the processing power to encrypt it. They don't have that today, so that's something that's going to have to be added. It also means every device is going to have a unique certificate. So how do you manage those certificates? How do you issue new ones? How do you revoke them? I'm going to talk a little bit more about that later. So the different layers to a secured system. So they're all very important. You know, last year we all heard about a big car company that got hacked with a vehicle driven off the road on 60 Minutes and all that. And there's many ways they could have secured that system to make it better, and at all these different layers. So it's, it's hardware, it's the embedded software, it's a network, it's a cloud, the apps. So I'm going to go through the ways you might do it for these different layers. And I'll highlight at each of these layers, where that car company could have taken steps that would have blocked it. It's not just in one spot, but it's in many spots. You don't want to depend on just one layer to do all your security. You really need to integrate them all. So first I'll talk about hardware. So one method we like to do is vehicle bus abstraction. So where the vehicle bus, the CAN bus or the LIN or FlexRay or whatever you're using, is actually isolated from the processor that controls the applications and the wireless interfaces. So in a worst case scenario, someone hacks in over your cellular network, they still can't get to the car bus networks where your safety, your critical control systems are. So we put an API between those layers where every message is encrypted, timestamp signed by application. So only authorized applications can send messages to the CAN bus. Besides security, it also makes software development easier for the application providers because they don't have to know about car-specific commands. They can actually just talk to that API and not worry about a specific vehicle architecture. You also want to integrate an HSM within one of those microprocessors to secure your keys, to ensure that your keys do not get overwritten or copied. Every piece of hardware with a microprocessor has a JTAG interface. So JTAG is used for debugging and troubleshooting during the development cycle. A lot of times that interface is left there after the product is shipped, and it provides a real opportune place for a hacker, if they have physical access to that ECU, to get into it and put their own code on that ECU to do whatever they want. So we recommend removing the JTAG interface completely when the product goes to production. Now, some folks are reluctant to do that because it makes troubleshooting a defective ECU more difficult. So if you don't want to remove it completely, so you have that capability to troubleshoot later, you can put security on the JTAG interface, so there's an authentication for any device that might plug into it. And that's critical to do. Another thing you want to make sure is use a secure bootloader. So the bootloader is a process that loads the operating system. Well, that bootloader should validate that the operating system is loading is the operating system that it is supposed to be loading. In that case I talked about before, where the hackers got into that vehicle, they loaded a new operating system onto the CAN processor, and the bootloader did not validate that it was a valid operating system, so it just booted it and ran it, which allowed the hackers to do whatever they wanted. But a secure bootloader would have prevented that. The bootloader should be read protected, so nobody can load a new bootloader on it, of course. In the operating system itself, you want to validate each application that is run on that twice. So we validate once at boot up. Every application gets validated that it did not get changed or corrupted. Secondarily, at execution time, we validate that it did not get corrupted or changed in any way. Another thing you can do, encrypt the entire file system. Now, we don't do that all the time because that does add a significant amount of cost to the unit. So it depends what we're doing and the requirements, whether we want to encrypt the entire file system. But it's something certainly advised if you have the resources to do it. Secure application environments, otherwise known as virtual machines. We use those quite often too, because oftentimes we are integrating applications developed by application developers that are not ourselves. So the OEM might have an application they want us to integrate. They might have used a third party to develop an application we might integrate. We don't have the source code of these applications, so we don't know how secure they are. So we run them within a virtual machine, like a JVM or a Linux container, to ensure that that application only has access to resources that we've dedicated to it. So if it goes wonky or tries to act something it's not allowed to, it gets blocked. It's not allowed to leave the little environment it's run in. So that's the hardware. So the network. So that same car company, the hack that they had an issue here where they didn't use a private network. Their devices were sitting on the public network, so any device on that same carrier's network could actually access it. That's a very, very bad idea. So we use a private APN. The car company has their own APM, so it's their own virtual cellular network. Their own private IP address space that is not internet routable. So the only things that can access that car directly is that car company's cloud. There's no direct communication to the vehicle whatsoever possible through the internet. So if everything has to go through the OEM's data center, of course that data center must be secure. So there's many standards for data center security that the finance and banking industry have established. Use those. Within the cloud itself, there's some standards-based authentication protocols used for the web these days that are very applicable to this. So OAuth is used for authentication, uses TLS for encryption. We like OAuth 1.0a. Doesn't require TLS, but it's best to use it with TLS. There's an OAuth 2 spec that's really not the next version of OAuth 1. It's a completely different spec that's really not that applicable to automotive. And then within the APIs itself, so session-based authentication, like what web browsers use when you go to your bank site, HTTPS, those REST protocols. So sessions can't be captured and replayed later. This is an overview of the overall architecture for the end-to-end security model. So you have the OAuth server for authentication. You have a policy manager for configuring policy this can be used for both over-the-air software updates and cybersecurity. You have a download manager that actually pushes the updates out into the content distribution network. The update manager resides in the TCU or in the vehicle that actually receives the update, unpacks it, does the validation that it did not get compromised or corrupted, interprets the rules files for how it should distribute this, and then the flasher does the actual updating of the ECU that you want to update. The main thing to get out of this, though, is that every step in this process, there's an encryption layer and an authentication layer to ensure that there's no hacking done on this. This is really based upon the OMA DM standard, which is developed the standards for updating cellular phones. So if you've got Android or Apple phone, it uses OMA DM. Had to be modified extensively to support vehicles, since in the vehicle world, the thing receiving the update is usually not the thing you're actually updating. It's going to go update something else. So security validation. So penetration test beds are very important. So at Lear, we have our own internal pen test group that we actually do penetration testing of all the devices we make. We also test the end-to-end system. So we don't want to validate that we're secure. We need to ensure that the entire ecosystem is secure. So we make the box that goes in the car. Somebody else is doing the cloud. Somebody else is doing the consumer apps. We have to validate the thing end-to-end. We use lots of hacker-developed tools. We participate at Black Hat and DEF CON and learn what all the greatest tools for hacking vehicles are and actually use those in our labs, as well as commercial tools. We encourage black box and white box testing. So black box test is like what a hacker would do, where they just have a thing they don't know anything about, and they try various methods into hacking it to see what they can find. The white box testing is where we actually give source code and design documents to the hackers and let them try to find holes in it. So it's really good to do a combination of both. We typically do the white box testing internally and like to use outside labs for the black box testing, because a lot of the outside test labs will use different methods that we haven't thought about, that we don't know about. So getting different versions or evaluations of that is really important. And as part of the design process, you really develop a profile of what all the possible threat points for your device is. And you really want to do this at the design time. And then your test team can develop a test plan to test against it. So SAE recently released a new standard called J3061 that describes the cybersecurity process for automotive. And we've implemented this throughout our organization, and I think everybody is going to or should have to. It doesn't define how you actually do the security, but it defines the process for how you develop a secure product. So it's a very good document for developing the review processes, the audits, the third-party evaluation, analyzing the tools, the threat points. It's a very good baseline that everyone should use. And the automotive ISAC was formed about a year ago for the automotive industry to get together to collaborate on security, so to share information about possible threats and possible solutions. This has been a very effective model for the banking and finance industry, and now we've applied it to the automotive industry. So today, it's only the automotive suppliers that are part of it, or the automotive companies themselves. But now they're opening it up to the automotive suppliers, and I think that's key, since the automotive suppliers are the ones that actually write the software and develop the hardware. Now they can actually participate in this process and share that information. So it's very exciting that that's going on now. So 3 holes in this architecture, or in security architectures in general that are out in the field. Firewalls. So most firewalls are static. They're not updatable. You can't change the firewall rules. Intrusion detection systems have too many false positives. Most intrusion detection systems have about a 5% false positive rate. You can't act on that in a vehicle. You don't want to stop a vehicle from working because you falsely detect something going wrong. So we have to get better about that. And then in-vehicle certification management. So in the vehicle, if we've got 30 different ECUs with certificates, how do we manage those? How do we update those? So I'm running out of time, so I'm going to fly through these. So the basic firewall architecture. So what you do is you put an input and output filter on every single interface to the outside of your box on your ECU. You do that before it hits the routing engine. In case of denial of service attacks, you don't want your routing engine to get overloaded processing and dumping those packets and not performing other vehicle critical functions. So it's important to put those filters before the routing engine. Intrusion detection, a combination of learned intrusion detection. So you learn what normal bus communication is like and create a profile for that, as well as policy-based, where you download a policy saying these are the things that must go through. And certificate management. So how you manage other certificates, there's really two big issues that makes this different from a normal PKI infrastructure. One, you have to have right to repair. Some states have right to repair laws, so you have to allow a consumer or garage to swap out an ECU. So that means you can't have the OEM manage those ECU or manage those certificates completely by themselves. And secondarily, you can't do it completely in the cloud because a car is not necessarily always going to be connected. Even though it might be a connected car, it's going to not have coverage at some time, so you must have a way. So we're proposing an architecture where we actually have a certificate manager inside the vehicle. It could be on the gateway or TCU or whatever, that will actually serve as a certificate authority for the vehicle. So it'll issue certificates to new ECUs. It'll manage the revocation list right in the vehicle. And just to summarize, block, authenticate, sign and encrypt, and log. And do this security at every single layer. Don't focus on every layer. If you want a secure system, you have to think about the full end-to-end system, not just your little piece. So I am out of time.
Okay, well, first of all, thank you very much, Doug. A round of applause, please.
Yeah.
So we've had some questions come in since you've been presenting. So maybe if we take it from the top. In your design philosophy, you stated one of your principles was sign or encrypt. Shouldn't the principle be to sign and encrypt everything by default?
That is ideal. But most of these ECUs in the car don't have a lot of processing power, and there's a reluctance due to cost to put a lot of processing power on every ECU. And a lot of these messages, you don't really care about the privacy or hiding that data in any way. You know, on the bus, you might be sending the RPM data. You know, who cares if that's readable? You just want to make sure it's coming from the valid source. So you don't really have to encrypt everything. If you just sign it to make sure it's coming from the valid source, it's good enough. Okay,
thanks for answering that one. How are you going to manage the extra overhead on the CAN bus for items such as timestamps and encryption?
Yeah. So when we're encrypting all the vehicle bus messages, that isn't going to work on a CAN bus. CAN bus is way too slow. So to get that future architecture, we have to move to higher speed buses. So that's when Ethernet buses and like that are going to be required, because the frame sizes are going to get way too big to do full encryption on today's CAN buses. So that's, yeah.
Okay, and finally, have you considered post-quantum threats to RSA and ECC, especially for key exchange and code signing?
Yes. That is another reason we're going to need higher speed buses, because encryption standards keep getting more and more. We need more and more encryption, which means bigger and bigger and bigger packets. So we have to consider that. ECC is very appropriate for in-vehicle communications. You know, we don't really take a stand on what we want to use there. We'll use whatever our customer requires, but it's going to require higher speed buses and more processing power. But fortunately, all the car companies are aware of the needs of security now, and they're willing to pay a little bit for it. You know, that was our challenge a few years ago. When we were doing this, we had all these security mechanisms, but it added cost to our TCUs. Car companies didn't care as much about security then, so they cared more about price. But that's flip-flop now, so which is a good sign for our industry.
Okay, Doug. Well, please give Doug another round of applause.
Thank you.